Today we will talk about testing strategies, that is given a software, when to test, what to test, how to test, and a general overview of different strategies that we use during testing phase. So why do we test, or why do we have this phase of testing? As we know, testing finds errors. When we test a piece of software, which could be a module, a function, or the entire system, we find errors. Errors are reported, or that the test goes through with software giving us the correct expected behavior. So testing helps us in finding errors or different kinds of failures if there are any, but it can be noted that it does not guarantee absence of bugs. So if testing does not report a bug, it does not mean that there is a guarantee that there are no bugs in a given software. So that is not possible unless and until we prove that the software is correct and it will work as per the requirement specification. So testing is done to find errors, and then we debug the software and plug the holes and test the software again. So it's a very important activity in software life cycle, and it's also a profession. Testers need to be experts in testing and applying different testing strategies at different points of time in software life cycle. So a popular view is that testing starts after implementation, but that's not correct. The activities of testing do not start after the entire implementation is over. In fact, it can start, or it has to start as early as possible during requirement stage itself. So one can have an early agreement upon the test plan at the requirement stage, and that is very important. What is going to be your test plan? How are you going to test your software finally when it will be built? So specs can drive a test plan. From the specs you generate a test plan, and then the test plan can be validated or can be debated upon with the customer and with peers. The test plan gets modified accordingly, the specifications get modified, and then you go back and get a new test plan if you have modified the specifications. So an early test plan also helps in improving your specifications. So the requirements team is more clear about what the customer really wants, what is the ultimate goal. When you point out, or when you get a list of your test cases and the test plan, and if you know that ultimately this is what you want to test the software for, you are more sure about your specifications. So specifications can be used to drive the test plan. For example, let's have on this piece of paper a specification in terms of a use case diagram. So all of us know what a use case diagram is. So let's take a case of a library system software in which a use case such as return a book is identified. Return a book. And who is the user? The user could be a person at the counter. Now given this use case, return a book, what should be a test plan? One might say that you can generate a test case where you return a specific book, that is an already issued book. Or you could have another test case where you try to return a book that is available for issue. That means in both these cases you are going to expect some behavior. What is the expected behavior? In case 1, when you return the already issued book, the status or the state of the book should change from available to issued, or in this case return a book from issued to available, and if the book was already available, then it remains available. Now we have got a test plan with us and a test case or with a suite of say 2 cases for a given requirement specification captured in terms of a use case, that is externally observable behavior of a system. Now once this test plan is there, one might find out that when you return a book, you have to also calculate the fine that is to be paid by the user if there is any. So that is missing in this. So once you identify a test case, you might identify some missing features, and then once you this test case or the analysis of your test based on your high level needs allows you to also think more about the requirements themselves. So you could now add a calculate fine use case here and say that return of a book uses the calculate fine use case. So now after that your test plan also changes. You want to also check what was the fine or what is the accumulated fine on the user's account, on the account of the user who just returned the book. So in this fashion we can see that the specs on the screen, we can see that the specs drive the test plan and the test plan drives, or the test plan drives the specs. Once you modify the test plan, your specs are also modified. So modification in the specs causes a change in the test plan, and a change in the test plan might also cause modification of the specs if you are adding new features or if you are identifying something new from the specs point of view, new constraints or new features and so on. So testing is used to find errors, and an early plan of the testing can help refine your specifications, and then afterwards when the software gets built, when your modules start appearing, testing has to be carried out. So the plan has to be implemented and carried out. So we will now see different aspects of testing, various high level strategies. So this is an example test case. Here we are trying to find out what is a test case. So a test case is described through the choice of inputs for the unit to be tested. So given a unit, you want to test that unit and you want to identify what are the inputs for the test case, and along with the test case, of course, you have to also know what are going to be the expected results of the test case. Now we have given a few examples on this slide about a suite of test cases for a given function. So you have a function int f that takes 2 input parameters x and y. So you have int f, so this is C syntax, and function f takes 2 parameters x and y, and the function compares the 2 numbers, the 2 input numbers, and it reports the maximum. So what should be your test suite? How are you going to test this function? So for example, you could have these 3 criteria. When x and y are same, x is greater than y and y is greater than x, are you able to get the right value as an output, as the output of this function? So for these criteria, these are some chosen values. So in your test case, you must have some concrete values. For example, x and y is same, there could be many possibilities, but we have chosen one specific set of values for x and y, 10, 10. X greater than y, you have chosen x to be 10 and y to be 8, y greater than x, you have chosen 2, y to be 2 and x to be 25. Now given these three tests, your function works correctly. That does not mean that the function will work correctly for all set of inputs, but you have now validated the function against these three cases, and your confidence in the software, in the function, will go up if it works correctly for these three cases. So now we can ask these two questions: what criteria should be used to design test cases? How are you going to design these test cases? So we identified three criteria here, which are with respect to the values, their types, and also probably the semantics or the context. What should be the ranges of the values and so on. So what are those different criteria that could be used to design the test cases, and what should be tested? Now in this case a function has been tested. What else can we test? Now we are going to look at some answers for these questions in the course of this lecture today. So let's look at the first question. What criteria should we use? Should the testing be done based on external behavior, that is based on the external observable behavior of the software, or should one see the code to design the test cases? For example, that we saw the use case based test plan, we had seen only what is observable from outside and designed a test case based on what is observable. But then should we not look into the actual code, the statements, the structure of the code, and design the test cases? So this is an important question that can give us two major classes or major approaches to testing. So one looks at the external view of the software or of a given artifact, and the other looks at the internal view. That means you are going to test a software based on what is there inside the software, what is the code, specific statements, it could be conditions and so on and so forth. So the two major categories that we derive from this question are black box testing and white box testing. So we can see here that black box testing is based on what is required from external point of view. So you are looking at the software units or artifacts as black boxes. You don't see them inside. So you are going to take an external view or a user's view. So if you are looking at the entire software as a black box, you are going to use the user interface and test the software. If you are going to look at one module inside the software as a black box, you are not going to see inside that module, but at the same time you have to test the module and you will have to generate some input parameters to the module and generate the context of the module. So at any level you can apply this strategy of black box testing, and this black box testing does not take into account the internals of the artifact that you have chosen at a given level. It could be the entire software, or it could be your module, or one class, or one instance, and so on. And then the second approach that we get based on the internal view is that of white box testing. So white box testing is based on the insider's view of the given artifact. So for example, you have the code with you. Now you want to check whether all paths in that given code lead to correct answers, or whether all branches are covered. You want to generate such test cases based on white box testing or the internals of a given module or the implementation. So you get these two different approaches, black box and white box testing. So we will look at these two a bit closely. So here we see that black box testing is also called functional testing. That is because you are going to mainly look at the functionality of the black box, how it is to be used as a black box. You are not seeing inside, you are not looking at the internal structure, only the externally observable functionality. So test the artifact from external point of view, and specs are used to generate test data. So for example, specs of a given module, what is the contract that a given module supports. For example, take this sorter, it sorts data or data items. The sorting function or the sorter would be taking some input and produces sorted output. How will you test this sorter? You might generate a test case based on this black box policy. That means look at only the input and the output, don't look at the code of the sorter. Don't try to test the integrity of the code itself. So only look at the input and output and generate your tests. So you are going to only sample the entire space through input and outputs of a given module or a black box. So here a simple test case could be a specific set of data as input and see whether the data item gets sorted. Data can also be generated randomly based on input types. Once you know the types of inputs, you can generate random data, and these random data can detect some class of bugs. So black box testing essentially looks at the modules or the given artifact as a black box, and you generate test cases based on the input and output, the input to the black box and the output or the behavior, expected output behavior from that black box. In contrast to black box testing, we have white box testing, which is also called structural testing. Here you test the artifact from internal or implementation point of view. So we can see that though you are going to test the artifact from internal point of view or the implementation point of view, you are going to look at every statement, conditions and so on. You won't be able to detect the absence of features from the software, because you are not going to see the externally observable functionality as such. You are going to look at the code and different properties of the code itself. So white box testing is not advisable or is not capable of detecting absence of high level features or functional features of software. So different techniques that are used are as follows. You could look at statement coverage. Each statement is covered in testing. So you generate test data such that each statement is covered, and then you see whether your code works or not, or whether it results in a bug. You are going to check the robustness of your code. Branch coverage. Each branch is covered. For example, when you have if then else, the if branch and the else branch both are to be covered and the code gets tested. So you are going to actually generate the input so that both the branches get covered, and then you are saying that both branches of this if then else statement have been covered. Another approach is path oriented testing. You are going to select data such that different chosen paths in the program are covered. So you look at the code more closely and generate the test cases and see whether your program works correctly. So you are not really basing your test cases on the externally observable behavior. So you are not really basing them on different features. So if there is something absent, you will not be able to detect. Whatever is present, that will get tested through your different inputs or through your different criteria or coverage measures that you use in white box testing. Now the next question is that what should we test? What should be tested? As black box, white box, should only the entire software be tested at once after the entire implementation is over, or should the software be tested as and when the programmers generate programs, modules, classes, tables, user interfaces, business logic units? So should the software be tested in one piece at the end of entire implementation, or should the testing go on during the implementation as and when the code is built? Should every small piece be tested before the whole is tested? So that is what is put down on this slide. What should be tested? Should only the entire software be tested at once through the user interface once the whole software is built, or should every small piece of artifact be tested before the whole is tested? So this is an important question, and that is going to give us different levels of testing. So one can carry out testing at different levels. So we can see the levels of testing here. The module testing, or a test of a module, is at the individual module level. Each module is individually tested. It is also called unit test. As programmers build their modules, each of them are tested individually. A tester could be assigned for every module. So as soon as the module is delivered by the programmer, the tester tests that module, and if the bugs are found, it comes back to the programmer for fixing of bugs. So module test or unit test is carried out for every module, every independent module. Then the second level of testing that you can get is integration level, or it is also called incremental test. So modules that depend on each other are tested collectively. Say as modules get added into the system, as they get developed, the dependent modules can be put together and one can carry out an integration test. So integration tests also could be carried out partially for the partial view of a system. For example, you may not have the entire software available, but still you can carry out integration testing for the modules which are available, which are built. And what is to be done for the modules that are not available when you do the integration testing? We will see that soon, but let us look at these different levels of testing. So we have got module level testing, that is unit testing. We have also got integration testing, that is incremental testing. As modules get added into the system, you do the testing incrementally, you can do the integration testing. And then third level, you can have the system test, that is your evaluation test. You can test the entire system. So once the whole system is built, it is integrated, you test the entire system. And finally you have the acceptance test, or it could also be called live test. For acceptance of software, usually the customer does the acceptance test. It can be done at developer's side and also at the customer's side on live data. Based on the acceptance test, you have the subsequent payments and so on. So we have these different levels of testing: modules, integration of modules, system, and the acceptance test. Within modules, you can go finer and you can look at statements, conditions, and so on and so forth in white box testing. So let us look at testing of individual modules. So if a unit or the module communicates with other modules, how to test that module independently? Given a module, if it depends on other modules. So for example, in this picture you have M1 and M2. M1 is ready, M2 is not ready, and now you want to test M1, but M1 makes a call on M2. How are you going to test M1? What will you do for M2? If M2 is ready, this becomes an integration test. That means you are going to test M1 by integrating M2 with it, probably by linking M2. It could be a library module, you can link M2 with M1, the actual implementation of M2, and then M1 can actually call M2 if it is ready. But if M2 is not ready, how are you going to test M1? You still want to continue or complete the module level test for M1 even if M2 is not ready. So you can employ an interesting technique to test M1 in absence of M2, and that is to employ a stub for M2. So stub modules are the replacers for the actuals. So, you have to write a small piece of code for M2 that will directly return the expected value, or that will have a filler for the M2, so that M1 can continue. The return value should be in the expected range by M1. So, if a unit or a module communicates with other modules, how to test it independently? You use stubs. In this picture, M2 has been replaced by stub for M2. So, M2 here, the stub is not the actual implementation of M2 if M2 is not ready, but the tester writes the stub for M2, or if the stub is available, it can be integrated directly with M1 and M1 is tested. So, M1 is independently tested at module level or unit level with the help of a stub for M2. Then you also require a driver for calling M1, for activating M1 itself. At least for, say, if you have a single module, once you want to test that module, you will have to put that module inside a program, you will have to write a main, you will have to generate parameters and call that module. So, that piece of code that actually makes it possible to instantiate this module M1, say for example it could be a class, or if it is just a function, you have to generate some input and call that function. So, what is that code that does the actual calling of M1 or instantiation or creation of M1 and then testing of that M1? Now, you have a stub for M2, but for M1, how are you going to issue a call? How are you going to generate a call to M1? The actual software that uses M1 may not be available. Another module that uses M1 is not available. Now, you will have to create a small environment so that you invoke a call on M1, or you instantiate M1 if it's a class, and then invoke those test sequences on M1 and see its behavior. So, that external or that external environment, that external entity that drives your test suite or that selected test cases on the given module for module testing is called driver. So, this driver is going to make a call on M1, send the input parameters as pointed out in your test case, and then get the output and probably log the output or analyze it based on what the driver is going to perform. So, M1 uses the stub for M2, M2 is not available. So, you have a stub and you have a driver. So, these two are very important mechanisms in testing of modules, drivers and stubs. So, we can see on this picture that one can use a driver for partial integration or partially integrated system. So, look at this driver. You have this driver is going to test two modules which are ready, so and two modules which are not ready, for which you have put stubs in the driver. So, M1 and M3 are ready, M2 and M4 are not ready. So, they have been combined by this driver. So, probably you have an assembly line there, a sequence. The data flows from M1 to M2, M2 to M3 and M3 to M4, and it comes out of M4. The input goes first to M1. So, you have a sequence of instructions or sequence of modules which are executed one after the other. In output of one module is coupled to input of another module and so on. So, in this particular sequence, M1 and M3 are ready, but M2 and M4 are not ready, but still you can complete the testing by the stubs for modules which are not available and the driver to combine all the modules, to integrate all the modules, to actually pass on the output of one to the input of another, and the input identified in the entire test case in the first, for the first module in this particular assembly line. So, this is one sequence, one possibility. There could be other structures in your module graphs, and accordingly you have to choose drivers and stubs whenever required. So, the yellow ones are the stub modules and the green ones are the actual ready modules. So, we are able to do an integration testing with this partially complete system. Two modules are ready, two modules are not ready, but even if they are not ready, we are going to develop stubs for them, and the stubs are integrated along with the ready modules. The ready modules do not know that M2 and M4 are not complete, because they still are able to accept the input and give you some output. That output is sent to M3. Now one has to write appropriate stubs for M2 and M4 so that you are able to test M1 and M3 as per your test plan. Now there are some interesting issues regarding these drivers and stubs. Let's consider two different cases of top down and bottom up integration. So let's see how do we test, or how do we carry out our testing plan. What should be our testing strategy for top down integration? So we have these 7 modules in this particular diagram, in this structure. Module A uses module B, C and D. Module C uses module G. Module D needs modules E and F. Now when we want to do an integration from a top down point of view, we will first test A, then we are going to test B, C, D, then we are going to test G, E, F after B, C, D is tested. So in the top down fashion we are going to integrate everything. So test the main module first, and then you are going to do integration test for subsequent modules. So in top down integration, first you develop the main or the central theme of the entire software. The main is ready, your remaining modules may not be ready. So only your main is ready, but B, C, D are not ready. When you are testing A, B, C, D may not be ready. But when you are testing A is ready, A is completed. Your main module is completed, but the function on which the calls are made from main are not yet ready. So how are you going to test A? So you will test A with stubs of B, C and D. So make stubs for B, C and D and then test for A, or test your module A. Now when B is ready, you can test B. Will you require a driver for B? You will not need, because A is ready. Similarly for C, you won't need a driver because A is ready, but you will need a stub for G because G is not ready. So you can test B, C, D with stubs of G, E and F, and drivers are not needed to test B, C, D because A was ready before B, C, D. So A itself is a driver for B, C, D. When the actual code itself is ready, the actual code that makes calls on B, C, D, you don't need drivers for B, C, D. Similarly, when you want to test G, E, F, you don't need any stub and you also don't need drivers because actual modules of C and D are ready before G, E and F. So when you want to test with top down integration, you have to look into the cost of stubs. You need the stubs for the lower levels when you want to test a higher level module, but you don't need drivers because the higher levels are ready when you go to lower levels. The higher levels themselves can be used as drivers. So these are some interesting points or interesting features of top down testing through top down integration. Secondly, we can compare that with bottom up integration. You test leaves first and then you integrate them one by one into the higher levels. For example, when you want to test G, what will you need? You don't need any stub because G does not make calls to any low level modules, but C is calling G. C is not ready, only G is ready, you are going to test G. When C is not ready, you need a driver for G. Similarly for E and F, you need driver for D. In order to test G, E, F, you need drivers for C, D and A. And when you want to test B, C, D, you don't need stubs for G, E, F because the lower level modules are ready, but you need a driver for A. When you want to test A, you don't need any driver nor you need any stub because all the lower levels are ready and A itself is the highest level module. You can test the highest level module directly, you don't need a driver, only for the highest level module. Otherwise for all the modules, when you are coming from the bottom upwards, you need the drivers for all the upper layers. So mainly you are going to account for the cost of drivers and stubs are not needed when you have bottom up integration. So, error in module A gets detected in the last stage because you are going to reach the main or the main thread in the software, the main control in the software only at the end. There is another important testing strategy called regression testing. So, we see that software undergoes changes. What worked earlier may not work again with changes to the existing. When we make changes to something that already exists, what we had tested earlier may not work again. So, you have to carry out the test cases again if there is any change, and the tested modules depend on what has undergone changes. So, it depends on the severity of changes and probably the variables that you change, the effects might be different. The effects or the dependencies get propagated to the modules which are dependent on the module that undergoes changes. So, some test cases are re-executed when changes occur in the software. Changes may be due to availability of new modules or changes in existing modules. So, regression testing allows you to capture these changes and asks you to redo the test cases for all the affected modules. So, you may have to carry out integration tests again and again as the software changes due to availability of new modules and changes in existing modules. Now, we will look at some techniques that are used to monitor the behavior of programs. So, during the testing phase, the program behavior is monitored so that a bug can be fixed based on the observed behavior. So, when you are testing something, what are you going to monitor? So, typically monitoring is important during the debugging phase. So, if you find that there are problems with your outputs for a given test case, you may insert these program monitors so that you can catch a bug, or during testing itself you add monitors and generate some of the values so that you do not need to repeat, you can save on some time. So, we are going to look at these monitoring techniques. So, different kinds of software probes are used for monitoring of programs. So, they are classified as documentation probes or standard error probes and exceptions and assertions for defensive programming. We will look at them one by one. So, you could have different documentation probes such as counters for loops, traces of variables, how variables change their values, logs for different function calls, how functions are called, what is the sequence in which they are called, then contents of messages. If you are having message passing, say message passing between processes, objects, we are going to look at what are the contents of messages that you are passing on. Then there could be sensors for specific conditions. For example, when minimum is reached or maximum is reached, last index is reached, and so on. So, these are different documentation probes which can be inserted into the program. And standard error probes and exceptions can be used. Standard error probes such as divide by 0, array out of bound, access on an uninitialized variable, or parameter argument mismatch, type mismatches might be available in a programming environment. So, some of these error probes are standard, they are given to you by the programming environment, but if they are not given, one could implement exceptions which are user defined at higher levels. So, if the programming environment does not support standard probes, user defined probes can be injected as exceptions. Then there is another important technique called assertions, and it is used as a defensive programming technique. So, what is an assertion? An assertion is a statement in the program for monitoring a specific condition during a program's execution. Assertions of different kinds may be used to check whether a given condition holds at a specific point in execution trace or throughout a specified scope. So, what does that mean? Let us look at an example. So, there are two examples at the end of the slide. First statement says that a plus b, the value of a plus b should be greater than 12. So, one might say that when the program reaches, when the program flow during execution reaches this assert statement at this point of time a plus b should be greater than 12. If it is not, then there is some problem in the program. The error should be detected. So one could have this assertion statement when the programs are under development, and when everything is tested well, validated against expected behavior and bugs are fixed, assert statements could be flagged off or could be removed from the program. Another example of assertion is on the second line here, last line in this slide. The second example, assert I is greater than or equal to 0 and I less than 10 in a given loop. So value of I should be 0 to 9. If by some mistake the value jumps beyond this range, there is a problem. Failure must be reported. So assertions are used as defense against errors. Defensive programming. When you are developing, if you first start with assertions, many of the bugs in the program will be caught early. So if you the idea is to start with assertions first, inject your assertions at appropriate places in your code, and then you write the code for a given object or for a given module for a function. So we can have different kinds of assertions. For example, assertions can be used as preconditions on inputs. So when you have different inputs for a given function, you check whether the inputs are in a valid range, whether the input is valid. You assert for the validity of the input. You write an assertion or the assert statement in the program. Different programming languages provide certain support for assertions. For example, C has the macro called assert. You can use assert.h and write assert statements, embed them in your program whenever required. You can write an assert statement just at the beginning of a function on the parameters that are sent into the function. So you are going to use assertions on the inputs. You can use them as preconditions or you can use them as postconditions. After the function is completed, just before you return the value, check or validate the value. Write your assertion on the post effect, a desired post effect. For example, if you have an operation such as push on a stack, after the code for push is completed, you have to assert that the size of the stack grows by 1 and the element has gone on top of the stack. So you can write appropriate assert statements as preconditions and postconditions. Precondition is before the actual business logic is completed, and postcondition is asserted after that business logic is completed. Then you could also have assertions as invariants over a given scope. A specific condition which always is true for the entire lifetime of the object or of the module. A stack with fixed size should have size less than or equal to its capacity. You can't have more number of elements than the static capacity, than the maximum capacity of the stack when the storage is static. So these invariants over a given scope could be of different kinds. Again, they could be class invariants. For a given class, you can identify the invariant conditions. They could be loop invariants. There could be module invariants for a module set of functions, or system invariants for the entire system. The conditions that always hold to be true for the given scope, for a given class, for inside a loop, inside a module, and for the entire system. So till it could be a class invariant, object invariant. When the loop is executed, during the lifetime of that loop, the invariant holds true. So one can use these assertions very effectively in program design and also carry them over into implementation using the assertion support provided by a given programming language. All modern programming languages now support assertions through different mechanisms. There are also higher level assertion techniques, higher level extensions to these languages which are available. There are many papers also available on assertions, how to use them, what different kinds of assertions are there and where should they be used. So this is an important technique for defensive programming. If you use an assert statement, one can catch bugs when the assertion detects the failure or when you fail to assert a given condition at that point of execution. Now, another question that we have to see is, how are you going to evaluate your outputs? Is the output of a test correct? One can either do manual validation, but it's a very time consuming task. You can generate all the data for a given test case, and human beings, testers, or probably the validators can go through each of the outputs that you have produced during the test, but it's a very time consuming task. Otherwise, you can also do the same automatically through test oracles. So, one can develop these test oracles to automatically test and validate against what is expected. And the testing strategies, the test specifications and the catalogs are to be documented, the plans are to be very well laid out, and one has to organize entire testing phase. So, as we have seen right from requirements to completion of the entire system delivery, we have to carry out some or the other activities that are related to testing. So, what are the objectives of testing? One can look at testing from functional point of view. Functional test, whether the software works correctly. This is one of our important objectives. The most important objective is to look at the functionality of the entire software. So, one looks at the input values and the expected results. So, functional testing is the most important, because you look at the basic functionality, the correctness of the software against the basic functionality expected out of the software. Then you look at the performance, whether the performance is acceptable. Different performance parameters have to be measured and tested against what is expected as per the requirements. So, response time, how much time does the software take in order to complete a specific feature? For example, when you want to return a book in the library, how much time does the software take? Does it take 3 seconds, 4 seconds? The response time, execution time, or this is typically the completion time of a given task. Throughput is how many transactions are you able to carry out. So, the difference between response time and execution time is that in response time you are going to look at the first, when does the first response arrive to you, and execution time is how much time it takes in order to complete your given transaction. Throughput tells you how many transactions or how many activities are you completing in given unit time. Then space requirements, how much space, how much memory is needed, what should be the disk capacity. So, one can generate tests and see whether you are exceeding your space limits, disk limits, spaces of different kinds. Then delays in communication. If you have communicating systems, they could be intranet or internet or different kinds of communication systems may be used. Hardware, there could be hardware communication in your system. So, all kinds of communication links are to be involved, and you test for performance of your communication. Then you want to look at stress test. So, you test for the effects of overload. You overload the system. How many users, how many records, how many machines. Does the system work when it's overloaded? Then you look at structural testing. You are looking at logical paths, branches, etc. You traverse them and test your software against the structure. This is mainly the white box approach. Then you have security tests, where you look at the security that is offered by the given software. Say for example, you may have password based security. You test whether it works, and then you also have to test against the penetrative usages. say, is the system designed so that hackers are trapped, or are there possibilities that there are trapdoors or there are different loopholes in the system so that the security, basic security, can be violated. So different kinds of security tests are to be conducted. So with these objectives, the test plan for module and subsequent integration tests is made. Then we hear these two terms, alpha testing and beta testing, quite often with respect to testing scenarios. So what is alpha testing? It's typically conducted at developer side by a customer. Developer observes while the software is being used at developer side, and the tests are in controlled setup at the developer side. And beta testing occurs at user sides. Software is shipped, or the product is shipped at end user sites, and many customers may test the product during actual usages. So we have these two terms called alpha release and beta release associated with these two different phases in the product's life cycle. So one can say it's alpha tested or it's beta tested and so on and so forth. So beta testing is typically live testing at customer site on live data. And then we will have a couple of points on debugging. So debugging follows testing, and the results are assessed, and if they do not match the expected, the cause of the bugs, the cause of this mismatch of expected from what was observed, is to be fixed. And various debugging aids can be used. For example, one can have memory dumps or program monitors, which we have seen earlier, checkpoints and logs, or there are tools available called debuggers. There are common debuggers which can be used on different on a specific executable format, but the executables can be produced through different programming languages. Or you could have debuggers which are integrated in the development environment for the given language. So there are different debugging tools available, and they provide some of these mechanisms. So debugging is an important phase where one has to carry out bug fixing after the testing is done, and then probably after debugging again you carry out the test and see whether you are now following the specifications, where your tests are generating the correct expected output. And some related issues are listed here. So testing is not really an activity that starts only after implementation. It can start early with software test plans based on the requirements. Besides implementation, that is code, outcomes of other life cycle phases are to be validated or are verified formally. For example, a requirements analysis, a design document may be validated through peer or customer reviews, and models may be verified through model checkers if formal modeling techniques are used. And there is another aspect of testing, or another new use that software practitioners have found, is driving the development by test cases. So that is called test driven development. So what is advised there is that one can create the test suite first, and then you carry out the development. So first you get the test, that is the test cases, and then you carry out the development. So once you look at the test first, you are more sure about what you are going to expect. So this is called test driven development. So these are some of the recent views on testing. So in this talk we have seen different testing strategies. We have gone through black box, white box testing, integration testing, and different issues related to modules, modular testing of modules, top down and bottom up integration strategies, and we have also seen different kinds of program monitors and discussed various related issues. Thank you.